Okay, everybody that wants to talk can now put on their mics and do so. Or maybe just make a broad general comment that it seems to me that this History of the Universe series is more like a history of the science as it's been sort of developed over the ages, which I think is actually a very interesting way of engaging way
Yes.
of putting it. I like it.
Yeah. It's been beautiful. It's lovely. Thank you, Derek.
Yeah. All right. Who would like to kick off with some comments? I think, this, what is reality? We just accept it. We can't do anything about it. This is what my eyes see, so that's what is real. But thinking about it, I think science has sort of reached the limits of what we can see and experiment and do and so on. So beyond what we found and discovered so far, becoming pretty difficult to work it out. So string theory doesn't seem to have worked, seems to have been a flop, sort of. So at these small scales, and I think I remember the stat, an atom, as I remember it, the ratio of the space around a nucleus is about, relative to the size of a nucleus, is about 1,000 to 1. And the same actually then, so in that nucleus, you've got neutrons and protons. And within the structure of a proton, you've got quarks. And they estimate that the size of the quark relative to the size of the proton is also about 1,000 to 1. So if you take an atom down to the space between quarks and the outside of an atom, you're talking about a million, 1/1,000th of the space is actual stuff being quarks. So, yeah. And then beyond that, is there anything beyond that? Well, that's fascinating.
I think in the end, we're all just basically electrical charges of some description, aren't we? Which repel or attract. That there is no solid matter.
Yeah, I think it was Feynman that said everything is actually just waves.
Mm.
So what we perceive as solid matter is just waves in a special configuration.
I think we just don't have a sharp enough knife to get between them.
That's right.
Well, maybe our grandchildren will invent a sharp enough knife.
Derek, I was just wondering, he starts off in a cave and people just seeing illusions of reality. And because we cannot observe beyond our own senses, it could be that we're in a cave. There's a whole lot out there that we can't even measure. Who knows?
I'm going to just share the transcript. Just jump to let's go to the summary. Yeah, so the first, just quickly repeat the gist of your point there, Elaine.
I beg your pardon?
Please repeat what you said.
Oh, no, it's just that he starts off in a cave where the inhabitants of the caves seeing illusions of reality. And I mean, we live in a kind of a cave because we cannot observe everything. There are things locked to us because we cannot even measure those events which our senses are not attuned. We don't even know how to look for certain things.
Yeah.
Because you get what I mean.
That's a good point. I mean, that's what I'm sorry, Derek.
Go ahead, Peter.
So I was just going to say that's he didn't mention dark matter this time, but what Elaine is alluding to maybe is dark matter. We can't measure it, well, yet. Doesn't mean to say it doesn't exist.
Yeah, by the way, I've been watching a very, very fascinating YouTube about this lady scientist who's got a different approach to dark matter, but it's very complex. There's a lot of science, a lot of formulas in it, but it makes a lot of sense to me. I was actually wondering if we couldn't bring that in somehow into this middle of this series, but I've still got to go through it all. I've only done some of it.
I could always fit it into study group if you like.
Yeah, I'll send you the link and you can have a look. But what I want to do is like what I do with this. I want to do the transcript with AI, and then I summarize the transcript with AI. And I think that summary will help one understand what they're talking about in that interview a lot more. But it's I like it that this. I think it's an Indian guy that runs a lot of these physics interviews, and I don't know what his qualification is in physics, but I think he's just like a layman, and the way he approaches the interview with these scientists who are very sort of deep into their work is, he gets them to explain each point in layman's sort of terms. And I like the way the whole thing is run by him. So yeah, I'll send you the link, Peter. I think you'll find it interesting.
Yeah, no, I think if it's relevant to this, as long as there's not too many equations.
Yeah, I think if I can just broadly sort of summarize what her approach is, it's that she came from a different sort of study, a different science thing. I can't remember, some sort of biology or something, but she was looking at the maths of it. And then she realized that her maths could be applied to dark matter and the way it's looked at and so on. And she essentially what she's doing is she's splitting assumptions that people make and separating it from what one can actually, what we factually observe to be real. And this, it actually opens one's eyes on the way one looks at dark matter. Because there's a whole lot of theories that people put forward, Mond gravity and different gravities and other different things. And she takes all this into account. And it's actually, she sticks to what she can mathematically calculate and say, right, this is due to dark matter potentially. And I think it's quite eye-opening. But anyway, I'll send.
Yeah, it sounds very
interesting.
I'll
send a couple of the guys the links, and you can think whether it's worth looking at. I think it's something different to anything I've ever seen before, and it makes a lot of sense to me.
Yeah, this is David. Two things is, I think when I had my eye up, they actually used sound to cut the extremely thin membranes with a sound device, I think, an ultrasound. And then the second thing is, electrons, as far as I remember, they had different levels. Now, how can they stay at a level if they've got the same charge, distant from the nucleus? So, just talking about the energy level of the different levels of the electrons spinning around. I was taught that you get 3 or 4 different levels, and it can jump from one level to another. Or is that
Teacher Elaine, can you just remind us what the term is for the levels that electron jumps between again? It just slips my mind for the moment.
It's called quantums.
Quantums, that's right. That's where quantum theory came from, and explained it was necessary to visualize a structure like that to explain certain behavior of light and stuff, I think.
Yeah, or even others, because every quantum leap between the different orbitals would emit a different frequency of light, which would give you your spectrum.
Yeah, so those jumps in frequency that were being measured needed to be explained by the quantum. So that brings it back really to the wave nature of an electron actually being the sort of thing behind the quantum.
So
When you get a harmonic at a certain of one frequency with another, that's, I think, the sort of genesis of the quantum.
So it doesn't affect the diameter of the atom, what we call the atom, having electrons jump from a low level to a high level, and when they jump down again.
No, I think that you mustn't actually. It's a bit deceptive calling it jumping a level because that gives one a perception of distance from the center of the nucleus, and that's not the way it works. It's not actually a distance from the neutron, from the nucleus. It's actually an energy level with a different frequency.
Yes.
And if an electron had to crash into an electron?
So the electrons are like in a cloud. I think they keep away from each other in the thing, but in the space around the atom, but they're zipping around at I don't know what speed. They're not sort of like a satellite, like a geostationary satellite having over Earth at all. They're zipping around at a major speed of knots. More like the light zipping around the Earth once every half hour.
And they are not colliding because all of them are negatively charged, so they are repelling each other and they're keeping their spaces.
Thanks for that comment. Sorry, who was that?
It was Gert Steenkamp. I'm just saying the electrons will not collide because they are all negatively charged and they are repelling each other, so they're keeping their distances in that cloud.
Yeah. It's a Brownian movement. But I was referring to the ultrasonic cutter. Perhaps we're trying to split the atom in the wrong way. How else but electrically can you affect the structure of an atom?
So I think that, go ahead, sorry, Elaine.
Yeah, you know the Pauling's exclusion principle determines that no two electrons may share the same quantum numbers. So in other words, they've got to have opposite spin and they cannot be in the same energy level. They're not allowed to be because then they would be similar. They would be occupying the same space. So they all, the wave nature determines that they have to be at a certain energy level. And that energy level, sorry, it's difficult.
Sorry, can I just get back to, if you just, Elaine, the first quanta level can have two electrons occupying it. And then from then on, the following quantum levels can have up to 8 per quanta.
6, I think.
Was it 6? Sorry, gotta remember my.
The first one is 2. That is what they call the S level. Then you go on to P level, which cannot
P level
levels, which is a total of 8.
Okay.
And then
right.
Yeah.
I knew there was an 8 in it somewhere.
Yeah.
But then those two, if there are 2 in the lowest levels, they've got to be differentiated somehow, as you say, by spin or something like that.
Yes, the spin.
Yeah. And then somebody's going to find out the whole thing was all wrong and we've got to have a different theory. Except that up to now, the theory seems to, if you translate predictions from the theory, they are pretty accurate in what we see in reality. So yeah.
Then what do you do with the electron or energy that has crashed, causing the shell, the electron to leave its shell and produce a photon? What happens to the other part of it?
So yeah, if you think maybe of those Feynman diagrams, there are photons produced when atoms sort of bits of atoms split out and crash into each other and so on and knock things out. Yeah, photons is one of the byproducts, and other things like what's the tiny particle with almost no mass called again? Not a neutron.
Or neutrino.
Neutrino.
Neutrinos, yeah.
And then I don't know. There are alpha particles and other particles. People like Pierre, they were here, would be able to explain to you what an alpha particle is. I think that's more like a, I don't know.
It's a helium nucleus, I think.
It's a neutron or something, yeah.
It's a helium nucleus.
Yeah, okay.
Derek?
Right.
It's up here. This 47-page attachment or 47-page document attachment, I must say I really appreciate the summary on the last 3 pages. It really helped to give some detailed perspective. Thank you.
The wonders of AI. What would normally have taken me 12 hours to do,
yes,
took about 2 minutes to do. Fantastic.
Thank you. And with that question just now, I thought you meant a valence. I thought those were the levels around an atom, but
that's correct. Yeah, that's what I was thinking of. Yeah.
Yeah, shells.
Yeah, the valence. You have the valence levels that the electron can jump up to with given additional energy. So
and when the electron jumps down,
then it emits a photon
and absorbs energy.
And it can absorb a photon directed at it and jump up to temporarily to a higher level. So that's when you have a spectrum with absorption lines and so on.
Isn't that something to do with Einstein's photoelectric effect or something like that?
He got the his Nobel Prize for the photoelectric effect.
That's correct.
Yeah, the photoelectric effect gets a current to flow by light bumping electrons around. Yeah.
That's right.
In fact, that's what our beautiful solar panels are all about. Yeah. All right. So reality. So we might all be simulations inside a big giant computer. It really boils down to almost is what you could say.
Well, that's the thing.
How do we know it isn't? That's the problem. So I mean, it's a good question, but to me, I can't worry about it every day. I just got to pretend everything's real.
To me, the whole thing about reality, it's almost a philosophical question.
Yeah.
We're trying to apply a scientific explanation to it. I don't think science can ever explain what reality is. It's a philosophical thing. Because, I mean, would reality exist if we didn't exist? If there's no one there to observe, is there a reality?
So maybe let's just jump right to the beginning. I don't know if I haven't got it on this one. I've got another one where I put in the time segments. But anyway, I think the next 3 segments are also about an hour, but I don't know. I'll have to check my sums in the times, make sure that don't go over the hour. We will either do part 4, 5, and 6, or just part 4 and 5 if it gets too long. I'll just see how it works out.
Yeah, I did wonder perhaps whether we should have finished at the first. Instead of covering the atom, it seemed a completely different thing, but it all obviously gets tied together when you complete the whole video.
Yeah, but on the other hand, sometimes it's good to overlap things where you then, just remind yourself where you started with the concept and then you carry on in the segment with the rest of the concept.
Yeah. Anyway, I thoroughly enjoyed it.
Yes. Thank you very much.
All right, thanks. I've got UFOs to go and look for and try and photograph.
I'll look as well.
All right.
Okay, Derek. Okay, everybody. Enjoy the rest of your evening.
And we'll see you next time.
Good
Yeah, thank you very much. It was lovely.
All right. Okay. Cheers.
Mm.
All right.
Right.
Cheers, everybody. Enjoy your
Yeah,
supper.
that was bloody good.